Hello guys, this is CodeNCode and this is fifth lecture of this basic algorithm series. And as we started in the previous lecture, we are going to continue that lecture. And in this lecture, we are going to count the cost of the ith cyclic shift, and we will be see how we'll be studying the algorithm using which we can calculate the cost of ith right or left cyclic shift, the cost of ith left or right cyclic shift. So before we start, we have this problem. The problem statement is you are given an array of length n, which is a permutation of length n. Permutation of length n means there are n elements, all of them are unique and are from 1 to n. So permutation of length 4, one of the valid permutation of length 4 would be 2 3 1 4. Okay, all of the elements are coming are appearing exactly one times. All of the elements are unique and the size of the array is actually 4. So permutation of length n means all of the elements are unique and from 1 to n. Now there are q queries. In each query you will be given an integer k and you will be asked to find the cost of kth cyclic shift. For simplicity, let's assume we are talking about right cyclic shift. Here the constraints are n can be as large as 10 to the power 5 while k can be as large as 10 to the power 18. So you see, number of elements in the array can be as large as 10 to the power 5, but k, which is the cyclic shift, can be as large as 10 to the power 18, and you can assume that queries are also 10 to the power 5. I forget to mention the number of queries here. Queries can also be as large as 10 to the power 5. So there can be 10 to the power 5 queries each time. They can be asked. They can ask you find the cost of kth right cyclic shift. The cost of ith cyclic shift I have already explained in the previous lecture. If you have no idea, just go and watch that lecture first, because that is kind of prerequisite for this lecture. Now the problem here is, if someone asks to find the 10 to the power 18th, the cost of 10 to the power 18th cyclic shift, we cannot actually perform cyclic shift, right cyclic shift of the array 10 to the power 18th time. Of course, you know this would result in TLE. So there must be a way to get around that condition. Well, there is. So one of the important observation is that if for a permutation of length n, there exists only n unique permutation after cyclic shift, or in other words, the k cyclic shift is actually equal to k modulo nth cyclic shift. What do I mean by this, or what do I mean by this statement? Let me show you with an example. So this is the input array 24135, which is a permutation of length 5. Now here see, the original array will be considered as 0th cyclic shift. I'm talking about the right cyclic shift. Now the first right cyclic shift would be this array. The second right cyclic shift array would be this. Similarly for third and fourth. Now what this statement says, there exists only 5 unique permutations. So these are the 5 unique permutation. There exists n unique permutation and here is 5. So there exists 5 unique permutation, and these are those 5 unique permutation. Now if you perform right cyclic shift one more time, that means you want to find the 5th cyclic shift for n is equals to 5. So you see, 5 modulo 5 is going to be 0. So what it means is that 5th cyclic shift is actually equal to 0th cyclic shift, and you can confirm it, because when you perform cyclic shift n times, all of the elements will go back to their initial state, and that is what is happening here. Now if you want to find the 6th cyclic shift, 6 modulo 5 is going to be 1. That means 6th cyclic shift is going to be equal to the 1st cyclic shift. So in total, if there exists for a permutation of length n, there will be only n different combination or permutation. 0 cyclic shift, first, second, third, dash dash dash, and -1. These will be the only cyclic shift that we have to consider. We do not have to consider the nth or n plus 10th or something like that, because every k which is greater than equals to n will correspond to one of these 0 to n minus 1 permutations. So basically k cyclic shift is actually equal to k modulo n cyclic shift. So how does this help us is that if k is equals to 10 to the power 18, but you know that n is equals to 10 to the power 5 only, so you can take modulo and the result would be k would be from 0 to 10 to the power 5 minus 1. That means you do not have to perform 10 to the power 18 right cyclic shift, but only 10 to the power 5. That is a relief, but not that much. But this is one of the important observations that you must know about the cyclic shift and permutations. Now what we are going to do, we will be first studying the naive approach to solve the same problem. We'll be looking or studying the time complexity of that naive approach, and then we'll be studying how we can improve upon the time complexity that we achieve using naive approach. So this, as you can see, a 0 cyclic shift means the original array. Now the cost is 3 because 3 elements 2, 4 and 1 are not on their corresponding positions, so the cost is 3. Here cost is 4 after the first cyclic shift. Here cost is 3, again 5, 5 and 3. These are the costs and these are the ith cyclic shift. I have represented the fifth cyclic shift as well, but we do not have to calculate the cost of the fifth cyclic shift because fifth cyclic shift is actually equal to the 0 cyclic shift. So we do not have to calculate for the fifth cyclic shift. We only have to calculate for 0 to n minus 1 cyclic shift. Now we have to find the minimum cost, right? So minimum cost we can achieve is 3, either by 0 cyclic shift or by second cyclic shift. All this time I'm talking about the right cyclic shift. You can consider taking examples of left cyclic shift. All of the thing that I will be teaching is applicable to both the left and the right cyclic shift. That is why I'll be only taking an example of the right cyclic shift, and for the left cyclic shift you can take an example by yourself. Now how do we calculate this, the cost of each cyclic shift from 0 to n minus 1? Well, it is really easy. So I'm assuming there are two different arrays, AR and cost. AR is the input array, which means this, and I'm using the one base index system. Now cost array is, of course, will store the cost of the ith cyclic shift. So now you run a loop from 0 to n minus 1, which is basically for each I. So we'll be calculating cost of the 0th, 1st, 2nd and n minus 1 cyclic shift. For each cyclic shift, of course, initialize the count to 0, run a loop from 1 to n. And if the jth element is not equal to j, that means j is not on its current position. That means you would increment the count, and the cost of the I cyclic shift is equals to count. And after that you would right shift the array. The right shift of the array would be this. So first we would be calculating for 0 cyclic shift, so we do not have to right shift the input array at all. So we have calculated it. We have calculated the cost of the 0 cyclic shift. After that we right shift the whole array one time. So when you right shift the whole array one time, this is what you would get. Basically you would get the next cyclic shift. So when the loop runs next time, it would calculate the cost of the first cyclic shift, and then you perform the right shift again, and then it would run again and calculate the cost of the second, third and fourth cyclic shift. So this is the naive approach to calculate the cost of the ith cyclic shift for each I from 0 to n minus 1. The complexity, if you see, and this you can, the right cyclic shift function you can define yourself. This is really easy to do so I'm not going to explain that here. Now if we study the time complexity of this algorithm, we see there is a loop which runs from 0 to n minus 1, basically n times. Now inside that loop we are performing some operation which are costly, like right shift. Can be done. To perform a right shift you have to traverse all of the array, so of course this would take big of n time. Similarly this runs a loop from 1 to n, so overall complexity is n square. So using naive approach we can calculate the cost of each cyclic shift, but the cost will be n square. So the overall complexity would be big O of n square. Now let's see how we can improve upon this time complexity. Now, to understand this thing better, to make you understand the algorithm that I'm going to teach you, first I have a question for you. For this is the original input array. If you perform the one right cyclic shift, you'd get this. And you see that after performing first right cyclic shift, 2 is on its correct position, right? So 2 is on that position where it's supposed to be. Now after one cyclic shift, I'm able to get 2 on its current position. Now you know that there are only from 0 to n-1 cyclic shift, the rest are redundant. So now the question here is find one more right cyclic shift on which 2 is on its current position, on its correct position. Now here one right cyclic shift I have already told. If you perform on this array, if you perform one right cyclic shift, 2 will be on its correct position. Now find one more right cyclic shift on which 2 will be on its correct position. Like you can say, okay, 2 is on its correct position on third cyclic shift or fourth cyclic shift or 0th cyclic shift. Just find one more cyclic shift on which 2 is on its correct position except first cyclic shift, because I have already told you the first right cyclic shift 2 is on its correct position. So just pause the video and try to find one more right cyclic shift on which 2 is on its correct position. I'm assuming you have done that and you have found no other right cyclic shift on which 2 will be on its correct position. The reason is that each element is unique, because we are talking about permutation of length n. So each element is unique. So there will be only one cyclic shift, either left or right. For right there will be only one cyclic shift, for left there will be only one cyclic shift. So for cyclic shift, for each element there will be only one cyclic shift on which that element will be on its correct position, right? So this observation doesn't seem that important, but this is the basis on which we are going to build our algorithm, which actually will run in big O of n time, not in n square time, which will be a huge improvisation on the time complexity that we have achieved till now. So how we are going to do that? First, let's look at one of the dumbest observation. So in the ith cyclic shift, if k elements are on their correct position, then cost would be n minus k, because total elements are n. Out of n, k elements are on their correct position, so n minus k elements will not be on their correct position. That is why the cost will be n minus k. Now to minimize the cost, we have to maximize k, of course. So we have to find such a cyclic shift on which maximum number of elements are on their correct position. This is the whole takeaway from these two observations. So this is pretty easy, right? Not a big deal. Let's do this. So for each element, if I can calculate the cyclic shift on which it will be on its correct position, after that I can actually calculate the maximum k and hence can calculate minimum n minus k. Now what do I mean by that is this. Suppose this is the input array. Now element 2 will be on its correct position after one right cyclic shift. You see, if you perform one right cyclic shift, 2 will be here, which is its correct position. So 2 requires one right cyclic shift to be on its correct position. Similarly for 4 requires 2 right cyclic shift to be on its correct position. You can see 4 needs to be here, so you need to perform 2 right cyclic shift for 4 to be on its correct position. For 3 we need to perform 0 cyclic shift because 3 is on its correct position. For 1 we need to perform 2 right cyclic shift, because when you perform first time it would be here, and then when you perform next right cyclic shift 1 would be here. So for 1 we need 2 right cyclic shift, for 5 we need 0 right cyclic shift. So if I ask you how many elements will be on their correct position if I right shift this input array 3 times, the answer is 0, because none of the elements need to be shifted 3 times to be on their correct position. So if the question is how many elements will be on their correct position if you right shift this input array 1 time, The answer is 1, because only one element, there is only one element which will be on its correct position if you perform one right cyclic shift. So if you have to find the maximum k, you can read how many, you see there are two elements which will be on their correct position if you perform two right cyclic shift. There are two elements which will be on their correct position if you perform 0 right cyclic shift. So since we have to maximize the number of elements which will be on their correct positions, we can see here the maximum k will be 2. Either you will perform 0 right cyclic shift or you will perform 2 right cyclic shift. So this information is enough to calculate maximum k. Maximum k is 2, because on some cyclic shift, say 0th cyclic shift, there are two elements which are on their correct position. So all you have to do is count the frequency of each element. One is appearing one time. That means one right cyclic shift will give you one element which will be on its correct position. Frequency of 2 is 2, which means if you perform 2 right cyclic shift, there will be 2 elements which will be on their correct position. Frequency of 0 is 2, which means there will be 2 elements on their correct position if you perform 0 right cyclic shift. That means to find the maximum k, you have to find the frequency maximum frequent element, and that will be your maximum k, and minimum answer will be n minus k. So k here is 2. That's why the minimum cost you can achieve is n minus 2, which is 3. Now the question is, how do you calculate the number of right cyclic shift needed for an element to be on its correct position? Well, you can calculate it. First let me show you using this. As you can see, if you perform 0 cyclic shift, there are 2 elements on their correct position. That means the cost would be 5 minus 2, which is 3. Similarly, you can confirm for 1, 2, 3 and 4. Now the question is how to calculate the number of cyclic shift on which the ith element will be on its correct position. So that can be calculated using this simple formula. For each element j, its correct position is actually j, right? So for element 3, its correct position is 3. So position, the actual position minus the current position plus n modulo n, this will tell you the number of right cyclic shift needed to perform for this element to be on its correct position. Now see, I want you to think about this formula on your own. Why do we need to perform this modulo is because of this. Suppose to calculate for 4, you can directly calculate it by the actual position, which will be 4 minus the current position. Current position of 4 is 2, so actual position is 4 minus 2. 4 minus 2 is 2, which is its correct number of right cyclic shift. But the problem is when for a number its correct position is before it. For example, for 1, its actual position is 4, but its correct position is 1. So 1 minus 4 is going to be negative, and we do not have notion of negative cyclic shift. So to calculate the actual number of right cyclic shift, you need to add n and then take the modulo of it. If j minus position of j is positive, then this j minus position of j plus n modulo n will be equal to j minus pos of j, which is correct. If the result is positive, that means we are calculating correctly. That means we do not have to add n. But if the result is negative, for example here the correct position is 1 while the actual position is 4, correct position is 1, actual position is 4, so 1 minus 4 is minus 3. So minus 3 is not none of the cyclic shift here, so just add n in there. So the result would be minus 4 plus 5, minus 4 I guess, minus 3, because 1 minus 4 is of course minus 3. Minus 3 plus 5 will be 2. 2 modulo 5 will be 2. We have to perform modulo. If you can check by yourself that okay, j minus pos of j is negative, just add n in it. Otherwise j minus pos of j is your answer. If you want to handle that by if condition, if else condition, then you can do that. Otherwise, if you do not want to handle it by if else condition, you can directly use this formula. So this is how you calculate the cost of for each element. You can calculate the number of cyclic shift required for it to be on its correct position. After that, all you have to do is count the maximum frequent element. The maximum frequency you have to count, and that will be your k. So the minimum cost will be n minus k. So this is how you will calculate the for each cyclic shift. You can calculate the cost of a cyclic shift. Now the overall complexity will be big of n, because for each element all you have to do is evaluate this formula. After evaluate this formula is of course takes big of 1 time, that means constant time. So for each element you have to perform this formula. So big of n times constant operation, so the overall complexity will be big of n. So this is how you can perform, or you can calculate the cost of every cyclic shift in big of n time. And the naive approach was taking big of n square time. So big of n is actually a really big improvisation on that time complexity. So this is how you solve this problem. And if you have any doubt or query, of course you can ask on the article that I have created for this course. So this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.